you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T with another math tutorial. Today we're talking about a new family of functions called the logarithmic functions, or log functions. Log functions are the inverse functions of exponential functions that we've just studied recently. In the next slide, we'll better understand the relationship between the two functions. But remember, inverse functions undo something. So if we were trying to undo, say, x squared, remember we take the square root of both sides of the equation. If we're trying to undo x to the fourth, we would take the fourth root of both sides. So taking the square root or the nth root is the inverse operation of squaring or raising to the nth power. So in this case, when we have an exponential function, if we are trying to solve for x, we will be taking the log of both sides of the equation. Since when we raise a base to a power, we always get a positive number, then the inputs to a log function must be a positive number. So the domain of a log function are positive numbers. You can't take the log of 0 and you can't take the log of a negative number. One of the most important things that you can understand to help you comprehend what logarithms mean is to understand this relationship. So we have an exponential function over here and the equivalent log function. So just remember, I've kind of color-coded here, but the base of an exponential function is the base of a log function. We read this as log base b of x. So log function is not a single function, it's a whole family of functions. It could be log base 2, log base 5, log base 0.3, log base e, log base 10, etc. So the base of a log is equivalent to the base of an exponential function. And notice here the x switches places and the y switches places. We'll practice doing converting between the two forms in a minute. But what you can see by transforming a log equation into the exponential function, when we say take the log of base b of something, what we are trying to determine is what power would I raise this base to equal this value. So for example, if I was trying to evaluate the log base 2 of 8, for example, what that's asking is 2 to what power equals 8? So we know that would be 3. 2 cubed is 8. So the log base 2 of 8 equals 3. If we tried, say, log base 4 of 2, we would be asking 4 to what power equals 2, and that would be the square root, which is 1/2. So our value would be 1/2. So log base 4 of 2 is 1/2, because 4 to the 1/2 equals 2. Understanding this relationship between exponential functions, which most of you have a good understanding of, and log functions will take the mystery out of these log functions. So here's a few more examples of converting from one form to the other. Now for now we're just doing the conversions, but in a subsequent unit or a subsequent video in this series, we'll be using this process of converting from log equations to exponential or exponential back to log to solve various kinds of equations. So remember, the base of the log function becomes the base of the exponent. And this is asking log to what power, so this is y is the exponent, equals 16. Now, we could use this to know that y is going to be 2. But for now, we weren't really asked to solve it. We're just trying to convert the forms. So here, 16, this value is an exponent. because the value of a logarithm function is an exponent. And finally down here it would be b cubed equals 8. So by doing this we would know that b must equal 2 because 2 cubed is 8. Now we could go the other way. We could start with a logarithm equation. So the base of this exponential function is b, so that will be the base of our log. So this will be log base 5. And essentially these numbers are going to change places. So we're taking the log of 125 and we're getting x. And we could calculate this to find out 5 to what power equals 125. Here the base is 9, so we're doing log base 9 of y equals 1/2. So again, these numbers are changing places in our equation. And finally here, log base b of 64 equals 3. So again, we'll be using this skill extensively when we go to start solving exponential and logarithm equations. Now, there are two commonly used logarithms, log base 10, which is referred to as the common log, and it's abbreviated by log without a base. So when you see log with no number here, no little subscript, that means it's a base 10. And also another common logarithm is log to base e. Remember the natural number that we used in our series on exponential functions. So log base e of x is abbreviated by ln of x. Now when we use calculators, there's a button for calculating the natural log and the regular logarithm, or the base 10 logarithm. There are not buttons to calculate the other logarithms, and we're going to be talking in the next slide about how we would do that. To calculate a log of some other base using a calculator, we have to use one of these two change of base formulas. So there's really two formulas here. You can use either one. So log base b of a is the natural log of a divided by the natural log of b, or it's the common log of a divided by the common log of b. So let's look at that to do a couple examples here. So for this, we could calculate the ln, or natural log of 5, divided by the natural log of 2, and using the calculator. So we've got here natural log of 5 divided by natural log of 2, and we get 2.32 if I round it. Now remember, that's saying, if we go back to logarithms, 2 to the 2.32 power is approximately 5. Now I put approximately here because I rounded that number. Now, we could have used this version of the form, so if I go and calculate base 10 log of 5 divided by the base 10 log of 2, I'm going to get the same number. So let's just show that we get the same. So log base 5, not base 5, log of 5 divided by the base 10 log, or the common log of 2, and we get the exact same number. So you can use whatever one you want. I wouldn't necessarily worry about both. Some calculators have buttons in different places, so some calculators getting the ln button is easier than the log button. On the graphing calculator, they're both easy to get. So on this one, we would be doing, say, the log of 5/16 divided by the log of 9. So let's see what we would get for that. So log 5/16. And to make sure you when you're using calculator, make sure you close that parentheses before you hit the divide symbol, otherwise you'll get the wrong number. So here we get negative 0.529. One of the things you would understand as we work with logs for a while, if you take the log of a number that's smaller than the base here, you're going to get a negative number. And when we take logs of numbers bigger than the base, we are going to get positive numbers. Now, one of the applications of logarithms is to what's said to be to compress data. So let's evaluate this column here. So the log base 10 of 1, again, that's asking 10 to what power equals 1, so that's going to be 0. 10 to what power equals 10 would be 1. This is going to be 3, and this is going to be 6. So you can see by taking the logarithm of this range of numbers that went from 1 to a million, we got a range of numbers from 0 to 6. So if we were trying to draw a graph of x values in this range or y values in this range, if we graphed instead the logarithms of those numbers, we would have a much smaller range of numbers. Now we could also use the natural logs. Now I can't do those so much in my head. Now the natural log of 1 is 0, but the natural log of 10 is about 2.3. Natural log of 1,000 is 6.9, 6.91 say, and the natural log of a million is 13.8. But again, the key thing is we're taking numbers that go from 1 to a million, so 6 orders of magnitude, and we are putting them into a range of about 1 power of 10. Now this property of logarithms gets used frequently in a lot of measurements that we use. So when you've read in the news or heard on the TV news about earthquakes that have happened in various places, they talk about the strength of the earthquakes using a number which is between, I don't know, it's always less than 10, so they're in the range of like 3, 4, 5, 6, 7. 7 would be a really big earthquake. This Richter scale is measuring the intensity or the amount of power in an earthquake, and those range of numbers would be quite large. So we use logarithms of the actual intensity for reporting, so it makes the numbers easier to understand. When we measure noise, we use something called decibels, and those also are calculated with a logarithmic scale. And also here, some of you have had chemistry class and you've measured the strength of an acid or a base using the pH scale. Remember that goes from, I think, 0 to 14. And any of you that are into astronomy, we talk about how bright a star is using its apparent magnitude. The key thing to keep in mind on these things is that they are logarithms. So if you hear of, say, an earthquake that was on the Richter scale of 4 and another earthquake of 5, that maybe doesn't sound like a big difference, but the earthquake of Richter 5 is 10 times more powerful than the one that was magnitude 4. So it makes the numbers easy to understand, but then it can be misleading in terms of small changes in these scales can mean quite large actual results. Now, when we're going to be working with logarithms, just as when we worked with exponents, we're going to have a series of properties of logarithms. Now, these properties all apply whether our base of the logarithm is base 10, so logs, or any other base. I wrote it here just for simplicity using the ln function, the natural log, log base e. So the log of any base of 1 is 0. Again, that's because any number raised to what power equals 1, and that would be that the question would equal 0. So the log of any of 1, no matter what the base is going to be 0. The log of a base is 1, so the more general thing of this is log, whoops. So the more general form of this is log base b of b equals 1. So that's kind of important. So if we took the log of 10, it would be 1. If we took log base 2 of 2, it would be 1. And the log of a base to a power, this would be base b here, is going to be x. So doing a logarithm undoes the exponential function. So these are some important properties to know. Also, if we take the log of a product, we could take the product and then take the logarithm, or we can take the log of each number separately, the x and the y, and then add them together. So log of a multiplication turns into a sum of logs. Log of a fraction or a ratio is the difference of the two logs. And essentially an extension of this property is if we have a log of some number with an exponent, the exponent comes to the front. Now when we're working with logarithms, sometimes we have a log of maybe a more complicated expression and we want to what's called expand it into multiple logarithms, but the logarithm of simpler things. And there will be other instances where we have multiple logarithms and we want to write them as a single logarithm, and when we go that direction we will be doing what's called condensing. So the next couple slides we'll work on some examples of applying these properties. So here we've got a number of examples for expanding and condensing. So first we would want to use the skill that we learned just before our midterm of rewriting a radical sign as a fractional exponent. And now we could use this third property over here, that the log of some expression to the nth power, we can bring the exponent out front. Whoops, I went the wrong way. So we could write this as 1/2 times the ln of x squared plus 1. Now none of the properties that we have deal with this. The properties only deal with the product of two things or the division of two things. So this would be as far as we could go. Now here we could split this up into the ln of the numerator minus the ln of the denominator. Again, I'm using this property right here. And now we have the product here, so we can use this property to expand that out. So now this would become the ln of x plus the ln of y, then minus the ln of 5. So again, on this side we are expanding it into simple logs. Here we can split this using the multiply rule into the ln of x squared plus the ln of x plus 1. This one we can't go any further, but here this exponent can come to the front. So we would have 2 times the natural log of x plus the ln of x plus 1. Now for now we're just practicing these skills of doing either condensing or expanding, and in the next video we will be using these to solve a variety of problems. Now sometimes we want to go the other way where we've got multiple logarithms and we want to end up with a single log as our answer. So our first step will be, if we have any coefficients in the front, to turn them into exponents. And now we can use the property that if you've got two logs added together, we can turn that into a single log of those two things multiplied together. Again, here we will take that exponent in on to that expression, and we'll take this 3 in. And now we'll use the property here where we have two logs subtracted. We can turn it into the log of a single item divided. So this would become the ln of x plus 2 squared divided by x cubed. So I hope this introduction to logarithms will help you and take some of the mystery out of these log functions, and good luck working your problems.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you